Okay, so we're going to talk about circuits and going to have some more math. You both see the chart. Did I share it?
No, I don't see anything.
Okay. Where's my share? How about now?
Yeah, now I can see it.
Okay. So we have basically two kinds of circuits, analog and digital. And we're going to save digital till the last class or next to last. An analog circuit uh, is just made up of a series and parallel combination of some active and passive components. Whereas a digital circuit are made up of combinations of binary logic components. So there's another one of these old scientist types called Kirchhoff that came up with a pair of laws, his voltage law and his current law. And these are kind of important when you look at any kind of circuit or connection of components to try to analyze it. And his voltage law says that if you travel around any loop in a circuit, the voltage across the elements add up to zero. He came up with his current law that says currents flowing into a node of a circuit must add up to zero. So what do those mean? If we have this circuit, which we call it a parallel, I've got that R1 in parallel with the series R2 and R3. And there's a battery, 75-volt battery that's supplied to the circuit. So there's 75 volts across R1. There's also 75 volts across the combination of R2 and R3. So that if I calculated the voltage across R2 and the voltage across R3, being V2 and V3, they would add up to be equal to V1 or the 75 volts. So if you try to apply Kirchhoff's law, if we start at the battery and try to go, let me see if I can remember how to turn. And I go in this direction, that I've got 75 volts here, but I have an opposite 75 volts in this direction. So they cancel out and the net is zero. Likewise, if I were to go around this loop, I'd have the same thing. I'd see 75 volts in one direction, 75 volts in the opposite direction. The net would be zero. The bottom line is in a parallel circuit, the voltage across all the parallel components is going to be the same. If I have this same circuit and I want to apply his current law, then it says the current flowing into a node, and in this case, a node is this connection, must add up to 0. So I have I1 coming into the node, or excuse me, I coming into the node. I have I1 coming out of the node. I have I2 coming out of the node. So I1 and I2 must equal I, which is this equation over here. So they have to add up to 0. So if I subtract I1 and I2 from I, it's going to be 0. The result will be 0. Any questions on that one?
No.
Okay. The main thing is in a series circuit like this, the current through the components is the same. Whereas in a parallel circuit, the voltage across all the components is going to be the same. So the voltages around the loop add up to 0. Parallel elements have equal voltages. Currents in and out of a node add up to 0. Basic Kirchhoff's current law and voltage law. So here's an example of a couple series resistors. We'll circuit with a voltage source and an ammeter, and we see that the current R1, okay, and the current R2 have to be equal okay, and we get 0.009 amps. This is just sort of the same thing, the voltage across each leg. Okay, so here's where the math starts to come in. If we have resistors in series, they add in value. In other words, if I have a series 100 ohm resistor and a second 100 ohm resistor, the equivalent resistance of the two is 200 ohms. If I put those resistors in parallel, so I have a 100 ohm resistor in parallel with a 100 ohm resistor, now the equivalent resistance of the two is 50 ohms. If I have capacitors in series, they decrease in value like resistors in parallel. If I put capacitors in parallel, they add like resistors in series. If I put inductors in series, they increase or add like resistors in series. And if I put them in parallel, they decrease in value like parallel resistors did. So the oddball is sort of capacitors. But the question is, when we have parallel components, how do we calculate the equivalent resistance? So if I've got series resistors, I just add them up. If I've got parallel resistors, I have to take what's called the reciprocal of the sum of the reciprocals. So in essence, I will take the reciprocal of R1, add it to the reciprocal of R2, add it to the reciprocal of R3, take whatever that total is and take the reciprocal of that, okay? And I'll get my 545.45 ohms. And I use the same values in both of these circuits. So when they were in series, I had wait a minute. No, I didn't use the same value. Yeah, I did. Okay. Oh, that's right. Okay. So one thing to see is that the result, this approximately 500 ohms, is less than the smallest value of the parallel resistors, which was 1K. So when they're in parallel, the result is always going to be less than whatever the smallest value of the parallel components are. This is just another example showing if I have a very small value, like 10 ohms, a 20,000 ohm, and a 1 mega ohm resistor all in series, that it's still going to be just slightly more than 1 mega ohm. If I take those, here I took 3 1 mega ohm resistors in parallel. So I convert those to the reciprocal of 1 over 10 to the sixth is 10 to the minus sixth. So I have 3 times 10 to the minus sixth, and take the reciprocal of it, or 333.33 kilo ohms. So it's less than, it's a third of the mega ohm. Now, if I'm going to do capacitors, if I put them in series, I have to do the reciprocal of the reciprocals. So the math is the same. I just calculate each of the reciprocals, add them together, and then take the reciprocal of the result. When they're in parallel, I just simply add them together. Just another example with showing a 1 microfarad capacitor, and you need to be familiar with these prefixes. And some of the test questions will be to convert from picofarads to microfarads and things like that. So I have a 1 microfarad, a 1 picofarad, and a 0.001 microfarad, which would be the same as 1 nanofarad. I find the reciprocals of those and then take the reciprocal of it. So I come up with slightly less than 1 picofarad, which was the smallest of the values. So it's just slightly less than that. When I'm doing them in parallel, I just simply add them. When I do inductors in series, they just add. In parallel, it's the old reciprocal of the reciprocals. So in this case, they were all the same, 3 somethings. Okay, so turned out to be 1. Now there's a trick or shortcut when you have things in parallel where you have to do the reciprocals. If they're all the same value, you can just divide it by the number of them. So if I've got 3K ohm resist or inductors in parallel, not ohm, microhenries, let's say, the result is going to be 1/3 of that. But it only works if they're equal values. Another example of inductors in series, we just add them. So in this case, I got 30 microhenries plus 3 microhenries plus 0.3 microhenries for a total of 33.3 microhenries. If I do those same values in parallel, oops, I wind up with 0.27 microhenries. So it's slightly less than the smallest of the values, which is 0.3. So remember, for series, I can add resistors and inductors, and I have to combine capacitors as reciprocals. And in series, the current is going to be the same through all the components. When I have a parallel circuit, I can combine resistors and inductors as reciprocals. If they're capacitors in parallel, I just add the value. And because they're all in parallel, the voltage is going to be the same across all of the parallel components. Any questions on that one?